Shall we start? I guess to start with, any question on homework two? Still on Friday? Oh, good. Well, yeah, sure, sure. Yeah, yeah. Yes. So, yeah, but I mean, I guess pretty much, the questions as you reach to the last one, you will get a sense that if you are doing right, you will get the right, no number in the end. So that's sort of, it will be graded by correctness, but you sort of also get a sense that whether you are doing the correct thing. Yeah, so they are all connected. If you do something like this and you think about this and check if your answer here make any sense. But for me, typically how I grade homework and assignment is that if you do it, usually you will get half of a point. So in whatever sense, just do it. Even you're wrong, you will get some credit for that. So submit something, even if you don't know what you're doing or it's obviously wrong, then just submit something. Yeah.
For that question 1.3, where you expect the hard max, essentially use
Which one?
like
Oh, this.
XF to find the corresponding frequency.
So
lost, like approaching that question because I tried plugging in XF.
Yeah, so the idea is to get this.
Yeah. Oh.
And we want the X for that. So it's not like looking at this and guess what this is, but rather, get this array and try to find the max. So if you do np.max, you get this Y value.
Yeah.
You do np.argmax, you get the X value.
Okay. And so we need to plug into np.argmax what we plugged into this part.
Yeah, I mean, basically what you would do.
And so in ELT.plot, there's I see two arguments being taken, XF, and then that equation.
Yeah.
What is the equation?
So this is the, you mean this?
Yeah.
Oh, this is just scaling the Y part. So so this is something tricky when you're doing FFT, because if the so this thing is sort of like just summing up stuff. So you have to divide it over the number of stuff that you sum it up.
Okay.
So it's just normalizing stuff. But generally we don't really care about the amplitude here.
Yeah. Okay.
Most of the time we're just, looking at the relative value.
But the maximizing aspect is that Y part, right?
Yeah. So you want to maximize Y, but you want to get the X that maximize Y. So, well, I mean, we could just do it here.
Like both these things, XF, and then the second argument into np.argmax.
So what you would do is that, well, we can just run it. I mean, there's no real harm. We just do it. Hopefully we'll get it done. Let's see. Well. Where am I?
What's the shortcut to run everything quickly?
Oh, Shift Enter.
Okay.
Yeah. So pretty much you just run Shift Enter all the way down to right before like where you start coding. So Shift Enter would be the way. And for the next homework, it's the same. Just Shift Enter all the way until you reach somewhere that you should be running or waiting stuff to run. Wait, how does it take so long?
It takes a while. The first time I did that, it took a while.
This is some network. Okay, downloading. It's not huge at all. Okay, anyway, I think it's usually the installation stuff. Because I'm using another account, so maybe that's the reason. Anyway, somehow. Cool. So assuming that we are somewhere here, so you get this YF and the XF. So the YF will be, we can just look at it. So this is the nice thing about So YF. So pretty much it's just a bunch of numbers. That's the value of these stuff. So this is like complex number. So to get the value of it, to get the magnitude, you want to get the absolute value. And that's exactly what we are plotting here. Or, if you scale it, it should be still the same stuff. Just that it's scaled differently. So what we want to get is sort of mp.max. Well, there's one more thing here. So, you get the max 0.0082, which is this peak. But what you want instead is the x. So that's what argmax will give you. So it basically says that, for this array, at position 5,582, you get the maximum value. So if you look at YF, and if you look at 5,582, no, YF, because you're looking at, yeah, I mean, XF is for the answer. So if you look at this, you should get 0.08. Wait a second. Let me see. Let me move this arc.
I thought you could index into XF on the final step.
Yeah. So this is what you get. So if you look at mp.max, you get like 0.008, which is the peak. So if you do argmax, you see 5582. So now if you plug in this 5582, and if you compute this, you will get the peak. So now you see that it's at the 5582 of that YF. But YF is different, XF is different from the index. So you have to also plug it into XF to get the actual XS's. So in order to get where this peak corresponds to, you would just do XF 5582, whatever this number is. You get 1046. So that's pretty much what we are looking for. So if you look at this, it's right at the position where that's sort of like 1046. So that's what I mean by MP dark max. And once you get the number, look at this plot, you should be able to judge whether your answer make sense or not. But pretty much this is what you want to go over.
Yeah. Can I take a picture of that? Is that okay?
Sure, yeah, I mean, go ahead. I mean, it's so you need.
Thank you so much.
And then you just look at what this frequency correspond to. Well, I don't know. MIDI, no number to frequency. Well, we can look at it. 1046. Where's 1046? So somewhere around here. So it's B sharp 5, 6, whichever. So that's how you get the value. So you will do it with another a short chunk of FFT. That's what you'll get when you are rounding this example, because you only get the first 20 millisecond. So if you look at the first 20 millisecond, it's just the first note. So you should know what that note is, because you can just listen to it. So pretty much what you get is this value. So somewhere around 500 to 1,000-ish. Cool. Any other question? I mean, just ask. We could just solve it in the class and everybody will nail it. Cool. Any question on this third part? All good. Cool. Just again, trumpet should be something that you're looking for harmonics. vacuum cleaner is not something harmonic, and drum kit is somewhere in between. That, you know, if you are playing the drum, you know, the drums, then you have that sort of like harmonic because it's pitched. But when you click the cymbal, you sort of don't get that harmonics. You usually get an impulse of a bunch of stuff. It's sort of like noise in some sense. Cool. Otherwise, I mean, it should be fine on Colab and shouldn't take too long if you want to compute everything. Should be usually you will wait a bunch of time when you are doing the import. But other than that, most you know, operations should be instant. Cool. For next week, we will do some GPU thing. So at that point, you know, Colab might be a bit tricky to handle. We will also have access to Great Lakes. I somehow figured it out how to do it so that each of you will get, you know, 500-ish GPU hours on our, you know, shared UMISH GPU cluster that you can use for assignments, but also for your final project. We will talk about it next week, but if you're interested in getting it started, could look into this website, where is the, you know, where we are, and then just do Great Lakes at the end. So you'll get a bunch of credits that you can access, but pretty much what you've done, once you go over this, you will sort of get something similar to Colab, but that's being run in, you know, the central GPU cluster. You don't necessarily need to use that for the next assignment, but you know, it will be better because Colab sometimes they will block you if you use it for, I don't know, like 6 hours a day. So you should be fine because the homework should be only like 1 hour-ish for even the GPU training. We tend to do the smaller model, but if you want to do it with final project, then likely you want something bigger. Cool. Well, anyway, this is not a coding class, but sort of just use Python to give you the sense what's going on. So the goal is to understand what's going on in STFD rather than actual coding. Cool, but you know, feel free to book a time to discuss. You know, don't worry about asking too many questions. That's what we should do. Cool. So due on Friday, homework 2, and I will release homework 3 soon. But we will be talking about it next week. We will go over it because there's a bunch of stuff that we should go over. Cool. So I guess we could again start with some quick recap. You know, we've been talking about what deep learning is. The goal is just to sort of give you some background knowledge of what these you know, black box model is doing. But you know, even after several years of studying neural networks myself, I feel like they are, you know, pretty much still black box. So the way you look at these, you know, formulation, how it works is try to sort of like, you know, in terms of using it, you still want to get a sense what it is about. It's sort of like, you know, looking at synthesizer, most of the time you just play with it. But if you do want to design a synthesizer, or you do want to, you know, create your new sound of it, then you sort of need to understand what's its internal working so that you can do something new. So that's sort of the same idea as neural networks. Think about it like a synthesizer, that sometimes you just don't care what they are actually built, but sometimes if you actually want to do something new with these model, then you sort of need to get a sense what's the internal working. Cool. So when we talk about this, I guess this is the most important concept for the last class, is that neural networks are parameterized functions. So people think about, you know, sometimes think about a neural network as some fancy, you know, intelligent AI, but the better way of thinking about neural network is that it's a function. It's a function. That's it. So, define your X, define your Y, define your input and output. It's just a function. It's a function fitting. So all the interesting, intelligent behavior like ChatGPT is something on top of that function mapping. So what it does for ChatGPT is to see what's the most likely next word follow in the previous words. But by doing that, it generates a bunch of words that make some sense and have some, intelligent-ish behavior. But in principle, neural network is just a function that map some inputs to the output. Cool. We talk about shallow versus deep neural networks, but we have that universal approximation theorem, which says, whatever function mapping, we can pretty much use one single hidden layer with a lot of neurons, then we can sort of approximate everything. But that's not efficient in terms of, number of neurons. So that's why nowadays people have structure in deep neural networks and, going deeper usually leads to better results, but it will become much harder to train these models. Cool. So this is sort of like a recipe. You experience it in homework 3 that, this is typically how you do machine learning training. You build a neural network and it sort of defines a set of function because initially you don't know what's the best weight for all these numbers. So it's just some, random mapping from your input to output, and it doesn't make much sense. Now you have to design the objective that define what's good for the function. And then you sort of use it to guide how you find the best, function. So, neural network is a set of different functions. They have, different, objective function value or, loss value or, goodness of their, the function. And the goal of deep learning training is to find the optimal parameters. So the idea is just sort of here, you have that function and you get something out, if you are doing, say, I don't know, dog versus cat classification, if you do it incorrectly, then you sort of want to improve this function so that it becomes better and better. So that's the core idea. So we talk about loss function. I'll just skip those. But basically what you want to do, we talk about L1 and L2 loss, in the simplest form, but, the idea is that you sort of want to get the absolute or square difference between stuff so that you can make the function better. And in real life, this is the actual form rather than, the simplest form at the top. So we have to sum over all the whole bunch of examples that you have. But pretty much it's just doing, aggregating average out the difference. Cool. So this would be sort of like a toy example of how we can sort of use deep learning to do classification. So this is actually what it's being done when you want to classify something. So think about, cat versus dog classification. Think about it on the other way, that we are doing binary classification rather than doing two-class classification. So let's think about it just like, is it a cat? So the output will be 1 if it's a cat, 0 if it's not a cat. So this is the simplest version that you can do some sort of this kind of idea. So that in this case, X would be, either some feature of say how many legs, does it fly, does it swing? But, pretty much some of the features that you have to use to determine whether it is a cat. Cool. So, neural networks, it will give you a bunch of, linear weights of stuff. So this Y hat, whatever that is, it will be a continuous value. So it should be some number from, negative 100, negative 200 to 100, 200, 300. It could be any numbers. So how we do it is that, remember that we have this sigmoid function that sort of like turns something into 0 to 1. So for 1 it's like more likely it's true, and for 0 it's more likely it's wrong. So that's sort of the idea how we do it in deep learning, so in logistic regression, is that instead of actually predicting whether this is a cat or not, we are looking into how cat it is and how not cat it is. And so the more it's cat-like, then you get something closer to 1 after the sigmoid. And if it's not something look like cat, then it will get a negative value that it will lead to something very closer to 0 after the sigmoid function. So that's how we do it. So you sort of like turn that into some numbers, and then you can train the models with this something called binary class entropy. You know, it's just some math. Look at it. It looks terrifying. But basically what it does is to push this model so that, the cat, if the input is more cat-like, then you push it to a 1. And if it's not cat, then you push it to 0. So this is just to give you a sense what the actual function is. And if you look at the function value of this, so if you plot this thing, negative log y, you get something like this. And it only makes sense between 0 and 1. So the goal is that if your ground truth, if this image is actual cat, then you want to drive this loss function down. And so it will move that your prediction to 1. And on the other side, if it's not a cat, then you want to move your prediction to 0. So that's sort of the way to think about these loss function. It takes different form, but what you care about is how to drive your deep learning model to push the prediction to where you want it to be. Any question on this? Sort of super math intense, but this is what's being actually used in the models. Cool. Because we can just move on. So sometimes you will see it like this, another terrifying form, but these two are equivalent. Sometimes very hard to judge why they are equivalent, but if you plug in y equal 1, then this term just cancel out. You get the first term. If you plug in y equals 0, then the first term cancel out, then you get the second term. But anyway, that's what you look at when you go to PyTorch and you do like nn.cross binary cross entropy, and you will see this formula. And pretty much if it's the first time you look at it, it's like, what's going on? You have no idea, but it's basically doing this. Whenever it's a 1, you want to drive the prediction to a 1. If it's a 0, you want to drive the prediction towards 0 by defining the loss function. So this is another form. So this is, we are doing cat or not cat. So it's like either 0 or 1. But now if you want to do multi-class classification, so this would be something we are doing in homework 3. Think about node instrument prediction. So, you listen to some sound, you want to classify whether it's a flute, it's a guitar, piano, whatever instrument. So a bunch of predefined categories of instrument. You want to predict which that is. So now you are predicting what's the likelihood or the probability that, say the first one would be piano, how likely it is a piano, how likely it's a violin, how likely it's a guitar sound. So to define the loss function for these, multi-class classification, how you do it is that you have to go through one additional layer where you sort of get something out. And what you want to do is to turn this, real value numbers at the last layer of your output into something that looked like a probability. So this is something we call softmax. Again, don't be afraid of the math. It's just some mapping. That's all we need to know. But so what's softmax doing is that what it wants to do, internally, what it's doing is that you take exponential of all the inputs, and then you sum them up divided by their sum. So basically what you get is some output that's sort of like, you get some input that's like 73.5, 2.6 minus 12.8. That's whatever your neural net will give you, whatever that is, some numbers that's like unbounded. And then after softmax, you will sort of get something like this, that sum to 1. So if this value you get is larger, then you will get a larger portion in the probability. So max is some way of turning a bunch of different numbers into a probability like things that sums to one, and that the larger the input is, you will get a larger portion in that output. So once you can do this, you can sort of imagine how you train this model is to maximize the correct category, maximize that number to one. Questions?
So you don't use the sigmoid at all when working with multiple?
No, yeah. So this is sort of like a expanded version of sigmoid. Yeah. Yeah, so this thing you can think about it like n-dimensional sigmoid. I guess that's a way to think about it.
And is sigmoid still being used in the earlier layers, like in the hidden layers?
Oh, yeah, but usually, as I said, that's the activation function. Nowadays, people are doing ReLU.
Oh,
But basically, yeah. So, yeah, so nowadays, what we do is, a bunch of layers, whatever that is, a bunch of layers. So each of these layers will be ended with a ReLU function. And you go through another bunch of layers. So all these will be ReLU. And if you are just classifying one single value, is cat or not, then you will get the sigmoid at the end, so that you get the sense. But if you are doing multiple class, say the animal. So the first one may be cat, the second one may be dog, the third one may be, I don't know, bird. Then you sort of don't do sigmoid at all. You just grab all of them and do this softmaxing so that you get something like, I don't know, say initially it would be 0.3, 0.4, 0.3. And then it doesn't look good because if your input is a cat, then you want to drive this up to one. So that's the goal of machine learning. And we will talk about how we did it, but this is the model. It is like, you can get something that sums to one. So it looked like some probability that you can, it's not probability, but you can sort of interpret it as, some confidence or probability or, how likely it is. Yep.
are you then applying the inverse, the cross entropy log function to each one of these? Y cap 1, Y cap 2, Y cap n?
Oh, you mean after this?
Yeah, after this.
After this, it will be, the ground truth will be 1, 0, 0.
Okay.
So cross entropy would be the whole thing here.
Okay.
So it's very, very confusing. So if you go to PyTorch, there will be cross entropy loss, there will be negative log, whatever. There's a bunch of different loss, but it just depends on, is your input this, and then you compute the loss directly, or your input is this, and then you compute the last part of the loss.
So then is the PyTorch function just doing the in-between step for you, or is it like?
Yeah, it would pretty much usually it would do the last part.
Okay.
You don't even need to do softmax. If you do softmax, then you have to use another function.
Okay.
So it's either I forgot exactly what the function name is, but it's like either softmax plus some PyTorch function, or you don't do softmax at all. Before softmax plus some other function. Then this, if you're doing the second function, then I will do the softmax for you. So it's hard to answer your question because it depends on the function that you're calling in PyTorch. But what you want to do is you get a bunch of numbers that's could be positive, could be negative. It's like unbounded, whatever, negative infinite to finite. And after this, what you want to do with your loss function is try to figure out a way so that it can be trained on something that's like 1, 0, 0. That it's a 1 in the class that you have. And how you do it is by first turning these numbers into something that sums to 1. And then you can compute, sort of like whatever loss function that is. You could do, absolute difference, square difference. But for this particular case, we are doing this cross entropy thing. I do have the formula somewhere. Well, that's the form. So again, pretty ugly, but basically this is sort of like an expanded version of this. So they are pretty much doing the same thing. If you look at it, it's like only one of them would be one, because in this case, y would be either 0 or 1. That's binary classification. For this, only one of them will be 1. So pretty much they are the same thing. Whenever you have the right class, you will get negative y, negative log y. Everything else will be 0. So it's sort of like driving the correct prediction to 1, everything else to 0. That's what this loss function does. Cool. So what the model is actually training, in the classification case is, either doing binary cross entropy for binary classification, or cross entropy loss for multi-class classification. So I guess you'll get a sense when you actually train something. But for now, the key takeaway is that regression is much more obvious, because you are just doing some generate some number and see how far away it is from the actual ground truth, and you try to push your model toward that number. But for classification, what you want to do is, for binary classification, it's that predict something, whether it's 0 or 1. So now the situation is not like just pushing them towards 0 and 1. You sort of wanted to make it into something that's more probability-like. And that's the same for class entropy. So you have to do softmax to turn them into some probability-like thing. And then you try to move them toward 1 and 0. Move the correct prediction to 1, move everything else to 0. So that's what softmax plus cross entropy is trying to do. Well, let me try to share the screen and hopefully it won't crash. So now we have this. So this is like the gradient descent of 3D case. I think this is a much better analogy if you want to think about what gradient descent does. So you can think about it sort of like raining in some sense. So now if you have some raindrop, so think about this is the way you want to get the loss function. So you want to figure out where the bottom is. So for each of these raindrop, it will look at, how the physics work is that look at the gravity and then look at which direction it will flow easily. So, in real life, it's guided by gravity. But, when we are doing gradient descent, is that at this point, look at the slope. Where is the fastest way to go to the bottom of the hill? So that's exactly what it does. Started with a very steep slope, then you start it very quickly, and then you just go toward it, and then you gradually smooth the position, and then somehow you end with that position. And then if you started somewhere else, you will sort of like just do a different path. But in any case, gradient descent should sort of like make it easy for you to reach the bottom of that direction. Cool. So if you started here, then gradient descent will just sort of like lead you toward this path, because this is the steepest path toward this point. And then at this point, you will realize that the steepest way is just go through the cliff. Any question on this gradient descent? Pretty much that's what we are doing in most of the deep learning model that we are talking about, how we train it, just doing this. Yeah.
In this case, what kind of minimum are we looking for? Because there's many different options here.
Yeah, we will talk about it. So that's the biggest challenge of deep learning. So we will talk about it later. But anyway, gradient descent will sort of guarantee you will get to the nearest local minimum. So you will get to some minimum, but that minimum is not the global one. The global one would be the sea level, right? So if you start here, you sort of end up with here. It's still better than that, but it's not the actual global minimum that we get. And later you will see that it's actually impossible for you to always guarantee the global minimum, but there's some way that we design. We will talk about it. There is different approach. One way is to sort of like shake this thing all the way. Whenever you reach here, then you just shake it. So think about if you have this model and you shake it and jump it towards some other place, at least it will be somewhere, maybe jump out of this cliff, then you can go to the bottom. So one way is to sort of like introduce some randomness in this path so that it's sort of like jump between them. Somehow you hopefully it will drop to another place. The other way is try to just change the landscape. So, we talk about skip connection. That's, we have that highway connection. That's a very good way so that you can smooth things out so that you don't have so many peaks and, complex landscape. But we will talk about it, but that's a very good question. So gradient descent only guarantee you to go to the localized minimum. So all the other tricks of all the, training stuff that we will see later is about how do you make gradient descent actually go to that global minimum that you want. Cool, but this is the goal. The idea is that assuming at some point, you know where you are going toward that. And so this is gradient descent. So, the core assumption here is that you have to know where to go at that point. And by that mean is we need to know what the gradient is. So previously, we always talk about, this is non-differentiable, so we cannot optimize this with deep learning. And that's exactly the reason here, because most of the deep learning model, we are looking into, gradient descent. So you have to know how to improve from your current position. That's the core of most, deep learning models we know about today. So if there's something that's, non-differentiable, meaning that there's no way you know where to optimize it, because, the slope is not continuous, so it will somehow like jump between different places. So gradient descent doesn't work in that sense. So for gradient descent to work, you need smooth functions. And that's why I think about the classification case, it's 0 and 1 classification. So can we just compute it with, either 0 or 1? That's not how it works. We have to smooth things out using sigmoid so that it turns into some smooth functions that you can optimize for. Cool. So this is gradient descent. This is what we want to achieve. But in principle, in neural networks, it's much complex. We won't go into detail how you do it, but this is something called backpropagation. So this is essentially what all these deep learning model is doing. And I would say it's very hard to understand it the first time you look at it. But every time I come back to something like this to get backpropagation, I have new thoughts. So I guess just get a sense what it is like, why we are doing backpropagation.
With MATLAB for AI, you can predict.
Wait.
Why wait? Start your MD this.
So this is just a very nice YouTube video that explain what gradient descent, what backpropagation is doing. But for now, think about it as a more efficient way of
because the cost
gradient.
function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here.
Well, any questions so far? So the idea here is that, what you want to do is to turn this like 0.5, 0.8, blah, blah, blah things. What you eventually want to do is something like 0, 0, 1, 0, 0, 0, 0, 0, 0. So gradient descent is to see how you can drive stuff so that you get closer to that. So you want this thing to be larger number, and you want all the other numbers to be lower. And you look at how you can achieve that. So one way is like increase the weight that with those neurons. But you can also look at the second one, and this is the key where we need backpropagation. So the the idea is that you want to change the number of these activation to drive what we need. And this is like to explain how you aggregate a bunch of different activations.
Here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing.
Cool. Anyway, I mean, again and again, you can just go back to this video. Hopefully, after homework 3, you will get a better sense, and then at the end of this course, you will get a better sense. But for now, backpropagation, think about it. It's an efficient way of computing the gradients that's needed for gradient descent. So think about it more like algorithm. Think about it like a clever implementation so that you can do these things on GPUs. So, well, I do have this animation. So what we do in training, that's why we need GPUs, and that's what's going on when you do that training thing. So what we call is that this is the forward pass, given some input, and you just compute the, some matrix multiplication plus weights, plus bias, and then you do activation, and then you compute the matrix again. So each layer is sort of like one matrix operation, and then all the way to the Y, that you get your output. So this is to, think about binary classification, to know what's the number. Is it 0.9 or is like 0.1 for the cat image that you have in the input. But it doesn't tell you how to make it better. To make, if you have a cat image, but it give you something like 0.1 for your cat classifier, then it's doing really bad. So you want to know how to turn that 0.1 to something closer to 1. So that's what backpropagation is doing. So, what essentially we want to do is the gradient so that we can do gradient descent. And by how we compute the gradient is that you can do this, something we call backpropagation. That's the thing that we saw in the video, that is sort of like guess what the desired change will be in this layer, and then you apply it to the previous layer. So, you look at these neurons, you guess, you try to see what is the, up or down for the value. You want to increase the value or decrease the value, and then you backpropagate to the previous layer to know what these number will be, so that you can lead to that increase or decrease of the value that you need. So we call this the backpropagation. The backward pass is that internally in PyTorch, there's some computation working. So you will see it in homework 3. At some point, once you do, y equal to model x, is that you are doing the forward pass, and then you compute the loss, and then there will be some loss backward that's doing this wrapping from the y all the way back to the x. So that once you have these red stuff, you sort of know how to tune all these weights and bias. And that's the gradient. You want to know how to tune each single weight and each single bias basically each single parameter in your model so that it leads to the desired change of your output. So push, 0.1, if it's a cat image, it's performing really bad, push that to a 1. Or, if a cat classifier, you get a dog image and it's something, 0.8, then you want to drop it down to 0. Questions? So, this is the loss backward you will see in homework 3. And internally, that's what's being actually compute on GPUs. So we need bigger GPUs, we need faster GPUs so that we can do this efficiently. Because think about how we do it. This is just one single step. You know how to move one step from your current parameter. So think about ChatGPT. There are billions of parameters. And at each single step, you're just tuning it, 0.00001. But somehow you want this model to be in the perfect step. And that's usually after millions or billions of steps. So each single step, if it takes 1 second, then you need million seconds. So it doesn't make much sense. And that's why we need GPU, so that this computation, and that's why we need backpropagation, so that this computation can happen in, less than 10 milliseconds for each step, so that you can update your model much faster. Cool. But pretty much you can think about it as a very efficient way to do gradient descent. So gradient descent is what we care about. Backpropagation is the way to cleverly make it faster and parallelizable on GPUs. Questions? This is the very technical part of deep learning training, but sort of get you a sense what backward is. And if you do machine learning training, you'll realize that this is the most time-consuming step. Everything else is fine. And this is the step where the GPU is doing all the computation. The forward pass and the backward pass, usually backward pass is still much more computationally. It's sort of equivalent, but that's the part that you need to compute so that you know how to tune your parameters. Yeah.
Are there ways to optimize a model or the way that it's designed so that it goes faster?
Yes. Yeah. So one way to think about it is that, again, think about that highway stuff. So if you have a highway from this X directly to the last layer, you sort of you can inference the stuff at the end much easier from the input. So that's sort of one way to sort of optimize your model. So we talk about network architecture. This is like the basic deep neural network. And soon, next week, you will realize that nothing we use today look like this. So there's a bunch of different connections, and there are that's what we call skip connection. That's like highway, and there could be loops, but all those are sort of trying to figure out different ways so that the models can be trained more efficiently, but also make it more expressive and match the assumption of the data. Yeah. So yes. Cool. Yeah. So I guess for the last 10 minutes, we can talk about some other ways. That's the ideal case. But in real life, gradient descent still won't give you the actual global minimum. You're usually stuck in some local minimum, like in the the random thing here. You will stuck somewhere here. That doesn't lead to the global minimum that we want. So, some of the tricks that you pretty much, if you are doing deep learning, most likely you won't be building anything from scratch. So, backpropagation is something like lost backward, and pretty much it's well, it just do the stuff for you. I mean, why do I need to know about backward? But, if you want to do gradient descent, there will be a bunch more stuff to be done. And these are things that we will likely be exploring when you are doing, coding in PyTorch. So the key issue of gradient descent is that it only finds a local minimum. So, we talk about that ideal case where there's just one minimum. But now if you look at this example, gradient descent will force you, it will lead you to somewhere just stuck in this local minimum at the right. But what we want is the one at the left, which is the global minimum. So, this is just like technical definition. Local minima is everything that's, sort of like locally optimized. And what we want is the global one. That's the minimum of all the local minima. So again, somehow wrong background, but this still look cool. Anyway, so there are several local minima, but what we want to get is the global one. So usually this is what we have in like a neural network. What we are training is something like this, that neural network is complex. There are multiple layers. There are different connections. So what we are actually optimizing is something like this. So that actually introduced a lot of issue when you want to actually reach this global minimum. You will easily stuck in some of these, dips anywhere. There are so many local minima. There's a local minima here. Well, I think I have a anyway. So local minima here, here, but also here you will see a local minima. If you stop here, it will just drop toward that. Think about it like raining. If you drop a water drop here, it will stop here rather than just flow through that. So to fix this, there are several different ways, and these will be some of the things that when you are fine-tuning your, when you are training your neural network that you would typically use. So first is, use an optimizer with adaptive learning rate. We will see some cool animation. So, we'll talk about it. The second solution is to use a stochastic optimizer. So that's something that I just talked about, shakes things up so that, if it's like water drops, maybe there's some chance that it will move to the other part of it and potentially go to something deeper. And the third one is that, well, we just change this landscape. This is very hard to train. Can we just make it smoother? But that required that you sort of change your neural network. We won't get into the many different things, but sort of give you some intuition why we are doing these different variants of stuff that you use in PyTorch. So learning rate and gradient descent. So if you think about it, the optimal way is that you somehow realize some learning rate that gives you this perfect convergence behavior that you just move smoothly toward that global minimum, local minimum. But if you are having like some smaller learning rate, it will lead to something like this, that each step you just move a little bit, a little bit, a little bit, and it's very slow convergence. But on the other hand, if you have a larger learning rate, it's much even worse, that it will just like jump back and forth, that at the end, at some point, you won't even reach the end. It will just jump and then sort of like just keep oscillating over that. So you lead to some low precision. And you can think about, even if we make it this larger, potentially these could go up if you have this learning rate too large. So sometimes learning rate will even explode, that leads to something that never converge. So the idea here, the main takeaway here is that finding the learning rate is very hard. Most of the time, you don't know exactly what exact learning rate you want. So this is the ideal case, but most of the time, you don't even know what your function is. Sometimes you lead to a smaller learning rate that's very slow convergence. Sometimes you lead to a large learning rate that leads to low precision. So all the optimizer that you will be using in PyTorch, originally you will use gradient descent, stochastic gradient descent, but most of the time nowadays you will see something like Atom, Adagrad, so different optimizer. So these optimizer is just doing different stuff. So one thing they did is called gradient-based adaptive learning rate. But the intuition is simple. So look at this. When you start it, so the blue one is the way when we do naive gradient descent. Just look at the steepest slope, and we just go toward that. And then somehow at this point, you will realize that, oh, okay, now this node turn this way so that you move toward this way. But that's not efficient. So look at the gray one, that's what we want. So, how it does is to look at, use a larger learning rate for the axis with smaller gradient. So when you started, these are the two gradients. So this is small, this is large, but you can sort of like independently do that. If this gradient is small, then you just turn your learning rate larger so that it also move diagonally. So that's sort of the key concept of adaptive learning rate based on the gradient. So that's what this optimizer is doing. So this is one way to do it. Second way is use momentum. So this is sort of like water drop also have this behavior. It's not like, you drop some water drop into some model and it will just stop at the point that you reach the optimum. Usually you will have some momentum that you just leave to somehow you can escape the local minimum. But anyway, these are two simple ways to sort of like give you some ways to make the optimizer better. But these are different optimizer. There are some momentum-based optimizer. There are gradient-based optimizer. So if you look at the one at the right, this is the loss function that we are optimizing. So look at the SGD. This is the naive implementation is sort of stuck here because at this point, there's no gradient at all. That's the point where everywhere is the same. So SGD will stop here, but if you have momentum, it will sort of like jump to it. And then for these will be gradient based, then it will increase the gradient to that axis that's much harder to train. But the optimal way nowadays, people usually just use this Adam optimizer. But anyway, we just talk about how it works. So Adam optimizer is typically the go-to choice for most cases. So nowadays, if you look at whatever model, usually at some point you will see this optimizer being used. But basically, it's just combining the idea of adaptive learning rate and momentum, the thing we talk about together. And it worked empirically well in complex neural network. So this is 2015, I believe, or 2012. 2015, I believe. And 10 years, and people are trying to beat Adam optimizer, but still, it's very hard to beat it. It's just performing really, really well. So anyway, these are a comparison of different optimizer. You can look at it. So usually people just try Adam at the first place. There's some local minima here that it will drop and stop here. Some of them, without doing fancy trick, it will stop there. But for a more advanced optimizer like Adam and RMS prop, it will easier to escape that. So, I guess the key takeaway here is that momentum gets you out of spurious local minima by, adding the momentum. So the model will explore around the local minima. It will much easier to jump outside of that local minima because you have some momentum going on. For gradient based adaptation is that you can maintain steady improvement on all the axes. If this axis is much harder to train, you have like small gradients, boost your learning rate to that axis. So it allows much faster convergence. Cool. Questions so far? Anyway, most likely you would just do like torch.optimizer.adam and pretty much most of the time it just works. And then somehow it just worked really nice. So that's what we would did in homework, what we would do in homework 3. But to give you the sense what's going on inside that single line of optimizer.adam. Yep.
Are there cases where the Adam doesn't work well?
Yeah, definitely. Well, usually it works pretty decently well. It's like, always 90% performance. And then there are some improvement on Adam. They're like Adam W. that sort of also has like weight decay. That's something we didn't talk about. But most of the time, Adam is pretty decent. I would say sometimes the learning rate, you would say it too large. But if you reduce the learning rate, I would say I never have any case that Adam doesn't work. So yeah.
Are there any advantages or disadvantages of RMS prop instead of Atom?
Well, in principle, they pretty much work the same. Adam has slightly better performance in general. It's very hard to define which one is better because it depends a lot on your neural network. So what people do is, just grab whatever, the most common neural network and just try these different optimizer, which one is better. And usually Adam is like constantly beating everyone else, or at least, good performance across different models. And that's why people are doing Adam. And Adam and RMS prop is pretty much, it's very similar. One disadvantage of Adam is that it requires a huge memory. You need more GPU memory for Adam optimizer. So for some of the optimizer, you don't need that amount of GPU memory. So nowadays, when you are training your model, think about backpropagation is that you go forward it. So you get one, say you need 1 GB to store all the weights. And then you do the backpropagation, meaning that you have to compute some additional stuff. So you sort of need another 1 GB to store those, gradient. So that's how you move your weights. But with Adam, you need another set of that to store what's being stored in Adam. So Adam actually usually require your backward pass to be 2 to 3 times more from your forward pass. That's the only downside. But nowadays people care more about performance than the size that you need for a GPU. Because GPU, you just buy larger GPU and you get a better performance. So that's what we do nowadays, use Adam. It has, much larger memory footprint, but that's only in the training case. So in training, use large GPU to train it, but in practice, you don't need to compute the gradient when you are doing inference. Cool. Very technical, but next week we will look at still technical stuff. But hopefully by the end of next week, we will be talking about the homework 3, which we will work on some real example. And you'll realize that everything I talk about is just one single line in PyTorch. It's pretty frustrating, but that's how it works. We should think about the high level stuff, but here's just to give you some idea what that single line is actually doing. It's a whole bunch of stuff going on under the hood. Cool. Homework due on Friday again, and I will likely release homework 3 by the end of this week. You can play with it, but pretty much we will go over it in class next week. Cool. See you Monday.